Hello again, students. So we are continuing with our study of projectile motion. Now, uh, when you are in the Army, or if you are in the Army and you've got some big gun, let's say a tank, and you want to figure out how far your cannonball is going to go, your shell is going to go, um, the way the information you have is which way the gun is pointed, right? How far tilted up the barrel of the gun is pointed. And so that's called the elevation angle. And so let's talk about how far your projectile will go based on this angle. Now, in the previous example, we were talking about something that was launched with an x component of velocity 4 meters per second and a y component 7 meters per second. And this angle right here, that would be the elevation angle. We've got the same velocities right here, 4 meters per second and 7 meters per second. And the angle is given by the arctangent or inverse tangent of the ratio of the two velocities, the y component and x component. So if you do this, you put in 7 meters per second and 4 meters per second. You divide, you get 1.75. You take the arctangent or inverse tangent, and you get your answer. It's 60.2 degrees. Continuing with the idea of, let's say you're in the Army and you're firing a tank, you have control over the elevation angle, and you may or may not have control over the overall velocity of the shell, but at least you know what the overall velocity is. So to continue with the discussion, we need to know, what is this overall velocity? We're going to use the Pythagorean Theorem, right? So what we do is we add this component plus this component right here. So what I'm doing is I move this vector over to the right so that it is now right here. So this is v0y. And then seeing that it's a right triangle, we use the Pythagorean theorem. And so we find out that the magnitude of v0 is the square root of the x component squared plus the y component squared. And so you get 8.06 meters per second. All right, so now that we've got the angle and we've got the initial velocity, we can now talk about the range formula. So how far your gun fires, that's called the range of your weapon. Okay, so here's our elevation angle. Here is our initial velocity, and the cannonball is going to do this path, and it's going to land at a place on the x-axis called x impact, but x impact is known as the range, r. Okay, so let's calculate the range. So the first thing that you need to do is to do this calculation is to know how long is the cannonball in the air. And okay, I forgot to say, but we are assuming no air friction, no air resistance. So the time that it's in flight is twice the y component of the initial velocity, 2 v0y over g. And now I actually am going to talk a little bit later about where this is coming from. The v0y, okay, is given by v0 times the sine of theta. So once again, if I move v0y over here, I'm taking this vector here, I'm moving it to here, and then this is my angle. This is the hypotenuse. This is the opposite side of the right triangle that's being formed. So the sine, being the opposite over the hypotenuse, is it's v0y divided by v0, and so so we have that v0y is equal to v0 sine of theta. Okay, so that's what we're using right here. Okay, so we have T impact equals 2 v0 sine theta over g. Okay, so now we know how long it takes for it to go up and back down and hit the ground. Now the range, or the x impact, is going to be given by the velocity component in the x direction times the time that it's flying. And now v0x is given by v0 cosine of theta, right? So let me change color to make it clear. So we're talking about this velocity component right here. And so we have, for this one, v0x equal v0 cosine of theta, right? So it's the adjacent over the hypotenuse. So Ka, C-A-H. So that's where that one is coming from. Okay, so so we've got v0 cosine theta, that's our v0x, and then the time, which is 2 v0 sine theta over g. Okay, now you multiply these things together. Notice we have v0 and v0. So that's where the v0 squared is coming from, right? Then you have the 2. Okay, so that's where the 2 is coming from. You have a g here. Okay, that's where the g is coming from. You have a sine here. Okay, that's where that's going there. And you have a cosine, and so that's where that's going. Now, there is a trigonometric thing that you can do to kind of somewhat simplify this formula. And here it is. It's one of the famous double angle formulas. So the sine of 2 times the angle is equal to 2 times the sine of the angle times cosine of angle. So 2 sine theta cosine theta gets replaced by sine 2 theta. All right, now let's get rid of some of this scribbling. R equals, this thing here is called the range formula. And this is also the range formula. So they both work, and whichever one you want to use is okay. Now, it turns out that the maximum range happens when the angle is 45 degrees. Why is that? So to answer the question, I want you to look at this one here. And right, so looking at that, you can figure out why that is. Think about it. Stop the video and think about it. I'm sure you can figure it out. Okay, so I'm going to keep going. Let's have an example problem. So I've got a cannon which fires a cannonball or a shell or whatever at 200 meters per second. What is its range if its elevation angle is 30 degrees, right, above the horizontal? And then what is its range if its elevation angle is 45 degrees above the horizontal? All right, so it's just plugging things in. We have our range formula, v squared over g times the sine of twice the elevation angle. I put in my initial velocity, 200, and don't forget to square, divide by g, 9.8, times the sine of 2 times 30 degrees, so that's 60 degrees. It's very easy to forget to square, and it's very easy to forget to multiply by 2. It happens all the time with my students. Try not to let that happen to you. And you get 3,538 meters, which is 3.538 kilometers, which is about 2.2 miles. So it's pretty far. Okay, so a cannon can shoot a long way. Now, what about 45 degrees? So you go through the same process, and the only difference is that it's 2 times 45, so it's going to be the sine of 90 degrees here. And you get 4,082 meters, which is quite a bit further than the original. It was 3.5 kilometers versus 4 kilometers. At this point, I'd like to go back to part of the development of the algebra and talk about where this came from, the T impact calculation. So let's go down to that part of my notes. So I said that T impact is equal to 2 times the y component of the initial velocity over g. And let's just be clear, T impact is the time it takes for the projectile to leave the ground and come back to the ground, and back to the same height as originally. So in order to understand where this thing is coming from, let's take a quick look at the worksheet that we did a few days ago. Here it is, straight up and down. So this was something we did in Chapter 2. So now, in this particular worksheet, there was a simplifying thing. Instead of 9.8, we're temporarily saying that g is 10 meters per second squared. And so here's this guy, and he throws a rock or a ball or something straight up. And at the beginning, the rock is going upward at 30 meters per second, and but it's decelerating. And after 1 second, it's lost 10 meters per second. So it's gone from 30 meters per second down to 20. And then another second later, it's gone to 10. And another second later, it's gone to 0. Now, as it comes back down, it's accelerating. So it's gone from 0 meters per second to 10 meters per second downward. And that's what the negative sign is for, to say downward. And then after another second, it's sped up to 20. And after another second, it's sped up to 30. So as you could see, there's this close connection between the time that's elapsed and the speed. So here are the velocity and distance calculations for various times. The example we were just looking at, so at 0 seconds elapsed, we have 30 meters per second, and we've gone 0. And after 1 second, anyway, we've got all of this information. At 3 seconds, it's stopped. The height that it got to is 45, although we don't really care at this point. But what's important is it gets back to 0. It gets back to ground level at 6 seconds, right? And so twice 30 divided by g, which in this case is 10, gives us the 6 seconds. We can do it here as well. So we start out at 40 meters per second, and as each second goes by, it loses 10 meters per second. It stops at 4 seconds, and then meanwhile we're figuring out how high it is. The maximum height is 80, and and here it's coming back down, and we get back to 0 at 8 seconds. So 2 times 40 is 80. Divide that by g, which is 10 in this case, and we get the 8 seconds. So I think that pretty much is why we have this particular formula. And I explained, what I just explained in words is what I just wrote right here. All right. Well, thank you. That's it for the notes on Chapter 4.